Hello, Tensor friends. I want to show something else here that I learned from Joe Hefner's sending me demos. I want to put a link to his website in the description. If you're a physics the teacher or student, there's a lot of good stuff on that website. So, and this is a way to show uh, how contravariance and covariance are related in a dynamical way. All right. So we have here a void. And in that void, we have a point. Okay. That's not what I want to do. I want to do that. That point now, as example, could be a particle. And this particle could have a velocity traveling in some direction, right? And the magnitude and direction of that particle we represent as a vector, right? So this is a mathematical construct, a geometric object we came up with to describe the velocity of that particle. So its velocity is however long that is, and it's traveling toward, as example, the northeast. Now, the way we describe that mathematically is we impose a coordinate system on that, right? So we have the coordinate system here, and we put a grid on it so that we can count things. That's the reason we did that. Because the particle doesn't know that we have a coordinate system, and it doesn't care. That's something that we did so that we could describe it mathematically. Now, on that coordinate, the system, we created these things called basis vectors, right? So here is an example: is the E1 basis vector is 1 unit long. The E2 basis vector is 1 unit long, and they're 90 degrees apart. Now we can use that to create an equation that describes this vector. And that's what we did yesterday by learning how to do superscripts and subscripts in the labeling part of Desmos, okay? So we can represent this vector as a linear combination of its components and basis vectors. And you see that our components are contravariant and our basis vectors are covariant. Now, when you have an upper I and a upper index and a lower index, that's an implied summation. We're obviously in 2 dimensions. So the first case I is 1, second case I is 2. So here is our vector. Now, what I learned recently was that we can put the actual values of these components and basis vectors. So this is V1, this is the magnitude of V1. This is V2 component, this is the magnitude of E2. And what's the magnitude of a vector? It's the square root of E1 dot E1, right? So you say, well, there's a cosine in that definition. Well, E1 dot E1, the angle is 0. What's cosine of 0? It's 1. All right? So now I can change the components of this vector, and if I do, I change the vector. So if I start moving V1, do you see? It is dynamically changing the component of the vector, and that changes the vector. So now this vector is 0 E1 and 1 E2, right? And obviously you can do the same thing to V2. But the law of general covariance, which is really what I'm talking about here, it says that if I change this coordinate system, I cannot change this vector. So this is a velocity. So the laws of physics must remain constant in any coordinate system. Well, how would I change this coordinate system, and how would I measure I'm not changing it? Well, the best way to do that is to look at the magnitude of this vector. So this is the magnitude of this vector v. And how did we find that? Well, this is a right triangle, yes. So it's 1 squared plus 1 squared equals 2 squared. That's the hypotenuse. That's the square root of 2. Okay? Now here's what I learned. You see that I define V1 the magnitude, this is V1, the magnitude of V1, V2, the magnitude of E2 as variables. Right, and here they are. This is F, C, G, and D are those four variables. And in LaTeX, if you put tick mark, $, then close the variable in curly brackets, then tick mark, it gives you the actual value it's calculating, which is, in this case, is this, right? So if I change A, it's changing this variable, this function that I created, F. And so it changes the number in real time, okay? So that's the point. Now, in order to demonstrate covariance and contravariance, what we want to do is actually change these basis to vectors. So look what I've done here. I put a scalar in front of each vector. So E1 has a scalar times it, and I've set them at 1 for now. E2 has a scalar in front of it. Now, what happens if I change the magnitude, which I'm doing that by multiplying it by a scalar? And so if you do that, you create a new vector, right? It's no longer the E1 basis vector. It's multiplied by a scalar. What if I double E2? Well, look what happened. The magnitude now is 2. So it's E1 dot E1, which is 4. The square root of 4 is 2. So that doubled, but the magnitude stayed the same. Well, how did that happen? Well, because in order to maintain general covariance, the component, the scalar V1, halved. So when this increased, this decreased. And conversely, what if I went down the other way? What if I went here? E1 decreased and V1 increased. Okay? So I thought it's really cool that you can show this right on the graph dynamically like that and start altering these things and show the student how covariance and contravariance works. So this changes against this contravariant. All right. I thought that was fun. All right. See you later.